Have you ever wondered why airplanes often take an unexpected curve, steering far away from what seems like the most obvious route across the ocean? What might look like a meaningless detour actually has more explanations than you'd expect. Are airlines trying to avoid something? It seems like a waste of time, doesn't it? Is there a secret behind these winding flight paths? You're planning a well-deserved break from work, real vacation time, somewhere far away, exotic and packed with adventure. Maybe Korea or Japan. Incredible food, rich culture, and endless opportunities to embarrass yourself by misunderstanding local customs. Sounds perfect, right? But as you were booking your trip to Asia, you noticed something strange. Your flight's route is taking a detour over Alaska. Wait, what? Why is my airline going so far out of the way to avoid the Pacific Ocean? At first glance, you might think it's a safety precaution. After all, the Pacific is the largest and deepest ocean on Earth. If an airplane runs into trouble over an endless expanse of deep water, finding a safe place to land won't be easy. Meanwhile, Alaska, while not brimming with international airports, is still a much better option than being stranded in the middle of the ocean. So, thinking it's purely about safety isn't entirely wrong. When pilots plan flight routes, they usually aim for paths that offer more airports along the way, just in case of an emergency. Emergencies are rare, of course, especially considering how many flights take off daily. But let's be honest, losing an engine at 30,000 feet over the Pacific Ocean is one of the most nerve-wracking scenarios I can imagine. Still, that's not the main reason airlines avoid a direct route over the ocean. The real reason? It's all about fuel efficiency and time. At the end of the day, an airline is a business, and its profits depend on how quickly and efficiently it can transport passengers from one point to another. Passengers are also in a hurry to reach their destinations, and airlines want to cut costs. So, finding the fastest route is a win-win for both. In short, and keeping things short isn't really my thing, speed is usually the biggest factor when plotting a flight route. Unless there are special considerations like avoiding jet streams or bad weather, the fastest route is generally the closest to a straight line. But hold on. Look at this flight path. It doesn't look anything like a straight line. Well, that's because you're looking at it on a flat map. But we all know the Earth isn't flat, right? It's easy to get confused because we're so used to seeing the world laid out on a 2D surface. Unless you're one of those rare people who pulls out a globe every time you need to see where a city or country is, chances are you're looking at flat maps. And on a flat map, this big curve that seems to avoid the Pacific makes the route appear much longer. But remember, the Earth is a sphere, or something close to it. Don't worry, we'll talk more about that in a bit. So, a straight line in 3 dimensions looks very different than it does in 2 dimensions. Let's do a little experiment. Got a globe handy? Oh right, most of us just use Google Maps these days. No problem, I'll use mine here. Imagine stretching a string from Los Angeles to Tokyo on the globe. You'll see that the string doesn't follow the lines of latitude exactly. Instead, it curves slightly upward, following the Earth's natural curvature. In reality, this effect would be even more pronounced because my globe is actually way too perfect. In other words, transoceanic flight routes often follow what's called the Great Circle, which represents the shortest path between 2 points on a sphere, like Earth. While the path may look like a curve on flat maps, it's actually the most direct route on a 3-dimensional globe. This concept of the Great Circle is widely used in aviation to minimize the distance traveled, resulting in fuel savings and reduced flight times. Even when a flight slightly deviates to avoid adverse weather conditions or radar-dead zones, routes are always planned to stick as closely as possible to the Great Circle. Using Great Circle routes becomes especially important for long-distance travel, like intercontinental flights, where seemingly large detours can actually save hundreds of kilometers compared to a straight line drawn on a flat map. Now here's the thing. Earth isn't a perfect sphere. It's slightly wider around the middle. When you look at photos of Earth taken from space, this difference is almost imperceptible because the planet is so massive. But believe it or not, if you measured Earth's circumference from pole to pole, it would be about 40,008 kilometers. Measure it around the equator and it's a bit larger, about 40,075 kilometers. Why does this happen, you ask? It's because Earth spins on its axis. Remember when you were a kid spinning super fast on a merry-go-round at the playground? That force that pushed you outward? Well, something similar happens to Earth as it rotates. Its middle bulges out slightly due to centrifugal force. And yes, Earth spins fast enough for this to happen. In fact, if you're standing on the equator right now, you're moving at about 1,600 kilometers per hour. Amazing, right? Those extra 67 kilometers in Earth's width might not seem like much, but when we're talking about the surface of an entire planet, that small difference becomes a big deal. This combination of two factors, the Earth's curvature and its extra diameter at the equator, means that a route curving toward the poles is shorter than flying straight, as shown on a map. But that doesn't mean airplanes never cross the Pacific Ocean. After all, people need to get to Australia somehow, right? That said, airplanes also cross vast stretches of water to avoid storms. While modern aircraft can climb high enough to fly above certain types of severe weather, like hurricanes and tropical storms, seemingly regular thunderstorms can be surprisingly challenging. With cloud tops reaching altitudes of over 18,000 meters, planes are instructed to steer clear of them rather than try to fly above or through. It's nearly impossible for a modern aircraft to be brought down by bad weather alone, but turbulence strong enough can injure passengers and crew as everyone and their luggage gets tossed around the cabin. So, the lesson here is always keep your seatbelt fastened. Another reason airplanes sometimes venture over the ocean is to ensure a smoother ride. Even in good weather, there's much less turbulence over water than over land. That's because the primary cause of turbulence is warm air rising from the ground. Water distributes heat much better than land, so flights over the ocean tend to be much smoother. Another critical factor in determining flight paths is air currents, more specifically, jet streams. These high-altitude air currents flow near the top of the troposphere. The troposphere is Earth's lowest atmospheric layer, where most weather events occur. The boundary between the troposphere and the next layer, the stratosphere, is called the tropopause. Its altitude varies between 6 and 19 kilometers, 4 to 12 miles, above Earth's surface. This variation creates sharp changes in temperature and air pressure, forming a wind tunnel that can reach speeds over 320 kilometers per hour, 200 miles per hour. These extreme speeds are most common during winter when temperature differences are greater, but even regular winds of 130 to 225 kilometers per hour, 80 to 140 miles per hour, are significant. So hold on to your skepticism. There are 4 main jet streams, 2 in each hemisphere, and due to Earth's rotation, they generally flow from west to east. The 2 most important for air travel are the polar jet stream, which forms near the Arctic Circle, and the subtropical jet stream, located closer to the equator. Both stretch thousands of kilometers in length, despite being only a few kilometers wide. Flying with the jet stream can shave hours off a trip, but flying against it can significantly slow down the plane. It's also worth noting the risks associated with jet streams. The biggest hazard is a type of turbulence known as clear air turbulence, which occurs along the edges of these currents. This type of turbulence is nearly impossible to predict and is much more intense than regular turbulence. While accidents caused by turbulence are rare, they can happen. One particularly serious incident occurred in 1997 when a flight from Tokyo to Honolulu suddenly dropped after encountering clear air turbulence. The pilots managed to regain control, but many passengers were thrown from their seats during the abrupt descent. The risk of fuel freezing is a critical concern for transoceanic flights, especially at high altitudes and when flying over areas with extreme temperatures. As airplanes climb, the surrounding air temperature can drop dramatically, particularly in Arctic regions or during winter, making the fuel susceptible to freezing. Aviation kerosene freezes at very low temperatures, so long flights over oceans may require adjustments in altitude to find warmer air layers. Additionally, fuel temperature monitoring systems alert pilots to descend if the fuel reaches a critical temperature threshold. To mitigate this risk, airlines often choose routes that pass through areas less prone to extreme cold when necessary. These precautions ensure that even on long flights over vast oceans, where emergency landing options are limited, the fuel remains stable and safe. With these risks in mind, flight plans must be carefully calculated to take advantage of jet streams without compromising safety. Understanding why planes follow certain routes often boils down to factors we don't usually think about in our everyday lives. Jet streams influence events tens of thousands of feet above us, and the curvature of the Earth only becomes significant when traveling hundreds of kilometers per hour across vast distances. I don't know about you, but my car isn't quite ready to handle any of that. At least, not yet.